everyone, today I will present the introduction and function modular of our project, the Grab Food Optimizer. As shown in the slide, food delivery services such as GrabFood are very popular today because they provide a convenient way for people to order food. In this project, we apply mathematical concepts to solve a real-world problem. The first concept is function, which is used to calculate the delivery fee based on the delivery distance. The second concept is graph theory, which is used to find the shortest delivery route between the restaurant and the customer. By combining this concept, our project aims to improve delivery efficiency, reduce travel distance, and provide a better experience for both customer and delivery riders. Next, I will explain the function modular. In this modular, we study the relationship between delivery distance and delivery fee. For our data, we selected several locations around UMK campus Kota Baru, such as McDonald's Bengkalan Cepa, Pizza Hut Bengkalan Cepa, Nesken Coffee, Maidin Kota Baru, Charagi Kota Baru Mall, KFC Kubang Korean, and Hasus Cafe Bacau. These locations were chosen because they represent different types of food and different delivery distance from the campus. The delivery fees is calculated based on a simple rule, where 1 kilometer equal to 4 ringgit. For example, 0.25 km corresponds to 1 ringgit, and longer distance will have a higher delivery fees. From the table, we define that set x as the delivery distance, which is the input, and set y as the delivery fee, which is the output. The mapping diagram on the right shows how each delivery distance is connected to one delivery fees. Each distance is mapped to only one delivery fees. Therefore, this is a one-to-one function. In real life, this means that when the delivery distance increases, the delivery fees also increases.
Hello everyone, in this section, I will explain the operation used in our GrabFood Optimizer, which are the composition function and the inverse functions. Firstly, we will define the delivery distance function of f of x equal x. This function represents the delivery distance between UMK campus Kota Baru and the selected destination. Next, we will define the delivery fee function as g of x equal 4x. This means that the delivery fee is Rm4 for every kilometer traveled. To calculate the delivery fee based on the delivery distance, we use the composition function. The composition function is g composed with f of x equal g of f of x. For example, our group chose the distance from UMK campus Kota Baru to Nesken Coffee Bengkalan Cepa is 5.5 km. So, we will use this 5.5 km substitute into the composition function. Finally, after the calculation, we will get the final delivery fee is Rm22. Next, I will explain the inverse functions. Sometimes we knew the delivery fee, but we want to find the delivery distance. So, we need to use the calculation of inverse function. Firstly, we start with the equation g of x equal 4x. Second, we set the y equal to 4x. Then, we make x the subject of the equations. So, x equal y divided by 4. Therefore, the inverse function is g inverse of x equal x divided by 4. We read g superscript negative 1 as g inverse. For example, if the delivery fee is 22 ringgit, g inverse of 22 equal 22 divided by 4 is equal to 5.5. This means we use 22 ringgit and calculate into the inverse function, and we will get the distance. So, this shows that the delivery distance is 5.5 kilometers. In conclusion, the composition function helps us calculate the delivery fee based on the delivery distance, while the inverse function helps us determine the delivery distance based on the delivery fee. This mathematical operation makes the delivery fee calculation more efficient and accurate. That's all for me. Thank you.
Next, I will explain the graph modular structure used in our project. This table shows the vertices table where each vertex represents a specified location in our delivery network. We label a location from B1 to B8 to make a graph easier to construct and analyze. B1 represents McDonald's Bengkalan Cepa, B2 represents Pizza Hut Bengkalan Cepa, B3 represents Nesken Coffee Bengkalan Cepa, B4 represents Maitin Kota Baru and Bronium, B5 represents Changi Kota Baru Mall, B6 represents KFC Kubang Korean, B7 represents Hasu Cafe Bachok, and B8 represents UMK Campus Kota Baru. These locations are selected as the vertices of our graph because they represent popular food outlets and important destinations around the Kota Baru area. By assigning each location to a vertex, we can create connections between them using h as distance. This allows us to model a route network and apply graph concepts such as finding the shortest path for food delivery. The vertices table serves as the foundation of the graph, while the relationships and distance between these locations will be shown in the h table. Next, I will explain the h table in our graph mapping. The graph consists of 8 vertices labeled from V8 to V1 to V8. The edges represent the connections between these vertices, while the distance indicate the length between two connected locations in kilometer. For example, HE1 connects V1 and V8 with a distance of 0.25 kilometers. Similarly, HE2 connects V1 and V2 also with a distance of 0.25 kilometers. Moving further, HE3 connects V2 and E3 with a distance of 5 kilometers, while HE4 connects V3 and V4 with a distance of 2 kilometers. Next, HE5 connects V4 and V5 with a distance of 2.25 kilometers, and HE6 connects V5 and V6 with the same distance of 2.25 kilometers. The longest path in this graph is HE7, which connects V6 and V7 with a distance of 50 kilometers. Besides the main route, there are alternative connections to V8. HE8 connects V5 and V8 with a distance of 8 kilometers, while HE9 connects V6 and V8 with a distance of 9 kilometers. This edges table helps us visualize the relationship between vertices and the distance between locations. It also allows us to analyze routes and determine the shortest or most efficient path within the graph.
Next, we analyze the hub in the graph. A hub is a vertex that has many connections to other vertices. This means it plays an important role in the network because more routes pass through it. By looking at the adjacency matrix, we can identify which vertex has the highest number of connections. That vertex is considered the main hub, and it is important because it can affect delivery efficiency. To make the connection clearer, we also represent the graph using an adjacency matrix. An adjacency matrix is a table form that shows whether two vertices are connected or not. If two locations are connected, we put a value in the table. If they are not connected, we put 0. This makes it easier to analyze the structure of the graph, especially when there are many vertices. Next, to find the shortest delivery route, we use Diskrit algorithm. We start from the source, which is V7, and we want to reach the destination, which is V8. At the beginning, we assign distance 0 to V7 and infinity to all other vertices. This means we don't know the distance yet for other points. Then, step by step, we update the shortest distance by choosing the nearest and visited vertex each time. From the table, we can see how the values are updated in each iteration. For example, in the first iteration, we move from V7 to V6 with a distance of 15 km. Then we continue updating the distance to other vertices like V5, V4, and so on. After completing all iterations, we can identify several possible routes. The first route is V7 to V6 to V8 with total distance of 24 km. The second route is V7 to V6 to V5 to V8, which gives 25.25 km. And the longest route is going through all vertices, which is 27 km. So, based on these results, the shortest route from the restaurants to the customers is route 1, which is 24 km.
In conclusion, this project shows how mathematics can be applied in real-life food delivery services. The function modular is used to calculate delivery fees based on delivery distance, while the graph module helps identify efficient delivery routes through the route network. These mathematical methods help reduce travel distance, improve delivery efficiency, and ensure fair delivery charges. Overall, the graph food optimizer shows how mathematical concepts can be used to solve everyday problems and improve modern delivery systems.
3